Now let's just move on further towards the question number 2, which says that a quadrilateral ABCD is drawn to circumscribe a circle. Then we have to prove that AB plus CD is equal to AD plus of BC. Now let's just see the figure first of all. Let us suppose we have this ABCD with us, which is nothing but a quadrilateral, and it is actually drawn to circumscribe a circle. And you can see there is a circle which is inside this particular quadrilateral, and thus we have to prove that AB plus of CD is actually equal to AD plus of BC. So let's just start the proof of this particular question. So first of all, we will start with the external points to the circle. So since you can see over here that from this particular point D, from this particular point A, from this particular point B, and from this particular point C, we have actually drawn the tangents to this particular circle. If I'm just talking about this particular point, this is an external point to the circle, and we have drawn the two tangents to this circle as DR and DS. And furthermore, from this particular external point A, we have drawn the two tangents to the circle, which is nothing but AS and AP. Furthermore, if I'm just talking about this particular point, this is again an external point to the circle, and we have drawn the two tangents in such a manner. And similarly with this particular C point. So what can we say about all these tangents? So we know from the theorem that whenever we will draw any particular tangents from an external point to the circle, their lengths are always equal to each other. So from that particular theorem, we can conclude that, let us suppose if I'm just using the concept that we can conclude from this particular point that since D, A, B, C are the external points, of the circle, then we can say that dr is nothing but is equal to ds. We can say about this fact that dr is actually nothing but is equal to ds. Furthermore, we can say that cr is actually nothing but is equal to CQ. We can say about this fact that CR is nothing but is equal to CQ. Furthermore, we can say that AP is nothing but is equal to AS. And further we can say that BP is nothing but is equal to BQ. We can say about this fact from the theorem. Let us suppose I'm just writing out the theorem. Using the theorem that the lengths of the tangents drawn from an external point to the circle are always equal. So using this particular concept, we can say that they all are actually equal to each other. Now let us suppose if I'm adding all of them. So let us suppose this is my 1, 2, 3 and 4. So let's just adding all the equations, what we are actually getting over here. So let's just see, dr plus cr plus ap plus bp is equal to ds plus cq plus as plus bq. So we have actually added the left hand sides of all these equations and the right hand sides of all these equations. Now let's just see what can we conclude from this particular concept. So first of all, you can see that let us suppose if I'm just taking a pair of this, I'm just taking a pair of this, and further I am just taking a pair of this and this. So let us suppose if I'll rearrange it, if I'm rearranging it, we can write it as ds plus of as plus of cq plus of bq. So this is my first arrangement and this is my second pair. So dr plus cr, let's just see dr plus cr. DR plus CR is actually nothing but this whole side, which is nothing but CD. So this is CD plus AP plus of BP. AP plus of BP is actually nothing but is equal to AB. So this is nothing but AB. Furthermore, we can see that DS, we have DS plus AS. DS plus AS is actually nothing but a sum of total AD length plus of CQ plus of BQ. CQ plus of BQ is actually nothing but is equal to the total side, which is nothing but BC. So hence at the end what we can say that AB plus of CD is nothing but is equal to AD plus of BC. So hence this is what we wanted to prove, that in this particular quadrilateral, which is actually circumscribing a circle, these two sides are actually is equal to each other. So this is nothing but the proof of this question number 2.